In this video, I'm going to explain how to calculate delay using shockwave and queuing theory. So let's first take a look at the problem here. It says figure 1, this one right here, represents the flow density relationship for 10 kilometer long stretch of freeway beginning at x0 and equals 0, ending at x3, 10 kilometer, which is subdivided into 3.33 segments. x0, x1, x1, x2, and x2, x3. A free flow Q enters the section at x0 and a constant ramp flow QR 400 vehicle per hour enters at x1 without delay. And it says since the ramp flow is not very large, the ramp has priority at the junction. Each of the three segments has two lanes with the combined capacity of 4,000 vehicle per hour and the flow density relationship shown in figure 1. The next downstream segment, x3, x4, is a bottleneck with capacity of mu equal 3,200 vehicle per hour. And the mainline demand is provided below, so this is the flow at x0. And it says estimate the total delay and maximum queue lengths using the deterministic queuing theory and the shockwave method. Estimate the speed of the shockwaves that will form. So I'm going to first start with the deterministic queuing theory and then jump to the shockwave method. So before we do that, let's first take a look at this problem here. This illustration right here, this is what basically the problem is explaining. So there is a 10 kilometer stretch right here divided into three segments with two lanes for the ramp flow coming in from here starting at x0. And there's a ramp right here at x1 with a constant flow about 400 vehicle per hour. And let's now take a look at this a flow density relationship. So as I explained in the other video, this left low density curve represents the uncongested traffic condition. So let's solve for this equation right here. So the equation goes Q equals V times K, which is flow equal speed times density. So let's plug in this data point right here. It'll be 2000 for the flow and V times 20 for the density here. And this will make the V equal to 100 kilometer per hour. And equation will be Q flow equals 100 kilometer per hour times K. So what it means that it basically assumes that the drivers in the uncongested condition will drive at 100 kilometer per hour with the free flow travel rate. So let's now finally start with the deterministic queuing. So first, deterministic queuing takes it into arrival rate and departure rate and get the differences in order to find the maximum queue length and time delay, and total delay will be between the areas between that on the curve. So first let's get the arrival rate at x3. So this is arrival at x0, but it didn't take into the ramp flow into account. So this is where the bottleneck x3 and x4, imaginary x4, where the bottleneck forms. So let's calculate the arrival rate. So let's write it down here. Deterministic queuing. So at x3, so arrival rate at x3 will be 3,200 vehicle per hour plus 400, that will be 3,600 vehicle per hour, and instead of 2000 it will be 2,400 vehicle per hour. And to calculate the when they arrive, it says 0 to 15 here, but for 3,600 you have to take it into how long it takes to get from x0 to x3. So it assumes that it moves at 100 km per hour and it's a 10 kilometer stretch. So if you calculate that, it will be 100 divided by, sorry, it's 10 kilometer divided by 100 kilometer per hour, which becomes 1/10 hour, and let's convert that into minutes, and it'll be it'll take 6 minutes to get from x0 to x3. So instead of 0 and 15 here, it'll be 6 and 21 minutes, and this will still be otherwise. And now let's calculate the departure rate. So departure rate will be x at x3t. So departure rate is equal to the bottleneck capacity of mu 3200, because only the capacity can get out of the bottleneck. So it will be 3200 3200 vehicle per hour, and we now want to draw these on the graph here, but before we do that, we have to convert these rates into the minutes, because right here is the horizontal axis in minutes. So if you wanna, let me put it in different color. So 3600 divided by 60 is 60 vehicle per minute, and 2400 divided by 60 is 40 vehicle per minute, and 3200 divided by 60 is, if you put that in the calculator, it gives you 53.33 BPM. And let's draw that here. So I marked 66 minutes and 20 minutes earlier, but keep in mind that this graph is I just eyeballed that it's not up to scale. So let me draw the rival curve in blue color. So it'll be from 6 to 21 here, and then it'll be at 40 vehicle per minute. So, and let me draw the departure curve in green. So it'll be 53.3 degrees. So let me label them. So it's 60 vehicle per minute, and this is 40 vehicle per minute, and this is departure curve is 50.33 vehicle per minute. And now we want to find where this point is. This is a point where it's called point of dissipation, where the Q ends. So in order to find this, we can set the equation of curve equal to each other and find the time. So let me write down the point of dissipation. So arrival rate equal to departure rate. So arrival rate down is first, it starts at 60 vehicle per minute. So it's from 6 to 21. So let me write down 21 minus 6 plus, then it's 40. The rate is 40 vehicle per minute, which is the point of dissipation, minus 21, equal to departure rate times t. Oh, wait, not departure rate, it's 53 times t. So this is 60 times 15 plus 40t minus 480 equal 53.33t. And then if you solve that, this is 900 minus 840 equal 53.33 t minus 40t be 140 equal 13.33 t. And let me put this in calculator. 140 divided by 13.33. So the arrival vehicle count will be 60 times 21 minus 1, and departure will be 53.33 times 21 minus 1, the same thing. So maximum Q will be A minus D, which will be 60 times 15 minus 53.33 times 15, which will be 900 minus, so this is 799.95, which should be rounded as 800. So it'll be 100 vehicle, which means that between this point, this will be 900. You write it down. This will be 900. And this will be 800. And the maximum queue length is 100 vehicle count. And if you want to also calculate the maximum time delay, you would get the longest horizontal point, horizontal distance between the arrival and the departure curve. So it'll be right here at the 900 vehicle count. There will be maximum delay. So let's calculate that here also. Let's write down maximum time delay at 900 vehicle. So we already know that at arrival curve is at 21 minutes, so we just have to calculate the departure curve minutes at 900. So it'll be 900 divided by 53.33, which is 900 divided by 53.33. It is 16.86. We can round it up to 17 minutes. And we have to add the 6 minutes because the curve is shifted to the right, which will be 23 minutes. So the difference between 23 minus 21 minutes is 2 minutes. So maximum is 2 minute time delay at the 900 vehicle count. So finally, let's calculate the total delay here. So total delay is calculated by calculating the area between arrival curve and the delay curve here. So these are the two triangles here. So I can calculate two triangles at once here because we know the base and height. So the height is right here, which is 100. And base is 6 to 11, 15. Another base at here, it's 7.5. So let's calculate the total time delay. So triangle is base times height times 1/2. So 1/2 times height times base, which is 1/2 times 100 for the height, and for the base it will be 15 plus 7.5. practicing calculator. So what is it? 1/2 times 100 times this 22.5 is 11:25 minutes, and actually it's the unit is vehicle minutes. But this is typically calculated in vehicle hours, so let's divide it into hour. So 1,125 divided by 60 is 18.75 vehicle hour is the total time delay.